Welcome to this episode of Real Chemistry. In this video, we're going to be talking about the pH of weak bases. This is different than calculating the pH of a strong base because weak bases only sometimes dissociate. That means that if you put a weak base into solution, only sometimes does it split apart, whereas a strong base will always split apart. So similar to a weak acid, here we're going to need to use an ice table. Before we get into a practice problem, let's talk a little bit more about a specific weak base and what it looks like when it enters solution. So here's the reaction between ammonia, which is a weak base, so that's a weak base right there, and water. Notice when it reacts with water, it accepts a proton. That's the definition, remember, of a Bronsted-Lowry base. And we generate NH4 plus and OH minus. This is what takes the pH of our solution up. So that OH minus is what we're always focusing on when we look at a base. Now notice it has an equilibrium constant over here, Kb. The B stands for base, and it's very small, 10 to the minus 5. That means most of our ammonia remains on the reactant side over here, and we just produce a little bit of OH. Let's take a look at what that looks like in solution compared to a strong base. So let's say that we have a beaker here of strong base. We put in, say, sodium hydroxide. And if we put in 3 sodium hydroxides, then what we get in solution is 3 sodiums, because they fall off, and 3 hydroxides. So pretty straightforward. Because sodium hydroxide fully dissociates, we get the same number of hydroxides in solution as we have sodium hydroxides. That's not true, however, if we take a look instead at a weak base. So now over here, let's take a weak base, our ammonia, let's put 3 of them into solution. When we do that, what's going to happen to most of our ammonia is it's just going to stick around as NH3, which wouldn't change the pH. Every so often, one of those NH3s will grab a hydrogen from water and make an NH4 plus and an OH minus. So notice here we put 3 NH3s into solution, but got just 1 OH minus. And that actually exaggerates the amount of OH minus we would have in solution. Really, only 1 out of like 10,000 of these NH3s is going to grab a hydrogen. So that makes our calculation a little different. Our main goal in this video is going to be, let's use an ice table to figure out what the concentration of OH is. So we want to find that concentration of OH. Once we find the concentration of OH, then it's relatively easy to calculate the pH. Okay, let's take a look at a problem. Here we want to calculate the pH of 0.45 molar CH3NH2. That's called methylamine. And it has a Kb, we're told, which is just the equilibrium constant for a base, of 4.40 times 10 to the minus 4. Okay, well, what are the steps in this process? First, I'm going to go ahead and write the reaction of my base with water. So we start out with CH3NH2, and that, which remember is a liquid. That'll be important in a second. And then we have equilibrium arrows, forward, backwards arrows, because there's a balance of reactants and products here at the end of the reaction. And our methylamine is going to accept the hydrogen, so it's going to become CH3NH3 plus, and that's going to leave behind OH minus, just like our ammonia reaction did. Okay, now we're ready to fill in the ice table. Here on the ice table, I have 3 columns. B, which stands for base, that's my methylamine. So that's that guy. BH plus, which stands for my conjugate acid over here, and OH minus, which is right there. So when I think about my initial concentrations, I know that initially, before any of this reaction occurs, I have 0.450 molar methylamine, and I have 0 BH plus and 0 OH minus. As the reaction proceeds, the concentration of base drops, the concentration of conjugate acid and OH minus increases. So at equilibrium, I'll have 0.450 minus X of my methylamine, X of my conjugate acid, and X of my OH. Now I want to write my expression for Kb. So Kb, just like any other equilibrium constant, is products over reactants raised to their stoichiometric coefficients. So my products are OH minus times my conjugate base, CH3NH3 plus, all divided by my reactants. Now I don't include water. Why? Because it's a liquid. So just like I said there a few seconds ago, the liquid state of water is important. That means it's not included in our equilibrium constant. Okay, now we're ready to go ahead and plug in our ice table results for equilibrium to figure out what that X is. So we remember that Kb is 4.40 times 10 to the minus 4. That's what we're told right up here. And that's equal to X for my OH times X for my methylamine divided by 0.450 minus X. Now here's a trick. Remember that if we have small Ks on the order of 10 to the minus 4, we can drop added or subtracted X's. You don't have to. You could keep the X and you would get the right answer. Actually, you would get a more precise answer. But we can drop the X, and that saves us a lot of time. So that's true for weak acid problems and for weak base problems. You can always drop that added or subtracted X. So what that gives us then is 4.40 times 10 to the minus 4 equals X squared over 0.450. Okay, now let's make that 450 a little neater, huh? 450. Now we can use some algebra and get rid of that 0.450 by multiplying it on both sides. And that's going to then give us 0.450 times 4.4 times 10 to the minus 4 equals X squared. Last step, we take the square root of both sides to get rid of that square. And we'll get that X is equal to 0.014. Remember that X is also our hydroxide concentration. And if we ever get to our hydroxide concentration or our hydronium ion concentrations, we're very close to getting the pH. So we've filled in our Kb with equations. We've dropped the added or subtracted X's, and we've solved for our concentration. Now the last step, we just have to solve for pH. Remember that POH plus pH is equal to 14. And that means once we get POH, we can go directly to pH. So how do you get POH? POH is equal to the negative log of my hydroxide ion concentration. So pH is equal to the negative of 0.014. So POH in that case is 1.85. And now, giving myself a little room over here, we can go ahead and solve for pH by using the fact that they add up to 14. So pH plus POH equals 14, which means that pH is equal to 14 minus POH. So pH is equal to 14 minus 1.85, which gives me a final pH of 12.14. Notice that that is a basic pH greater than 7. And that makes sense because we're solving here for the pH of a base. So that's how you can solve for the pH of a weak acid or a weak base. The only difference there is that Kb or Ka and what the hydrogen ion is doing. So once you can do this process, you can do it for either a weak acid or a weak base. All right, thanks for watching this episode of Real Chemistry. You can ask any questions you have below or subscribe.